Hello class, welcome to this unit on polynomial functions. So this is the first lesson of the unit, and in this unit we're focusing exclusively on key features to be able to sketch graphs of polynomials. So our essential question, how did the key features of a polynomial function help you sketch its graph? The learning goal is to be able to predict the behavior of polynomial functions based on these key features, and the standard is to be able to interpret key features and sketch graphs showing key features given a verbal description. Some of the key features include intercepts and behavior and so on. So here's a vocab for the lesson. You need to be able to describe the degree of a polynomial, the leading coefficient, polynomial function, relative maximum and minimum, standard form of a polynomial, and the turning point. Alright, so the standard form of a polynomial shows any like terms that are combined and the terms by degree in descending numerical order. So an example of a polynomial is 3x to the fifth minus 4x squared plus 2x minus 5. Now in this example, the leading coefficient, which refers to the non-zero factor multiplied by the greatest power of x, in this case the leading coefficient is 3. That is the coefficient or the number that is multiplied by the greatest power of x. The greatest power of x is 5, so this is my greatest power. And this is referred to as the degree of a polynomial. The degree of a polynomial is the greatest exponent or sum of exponents, if there are multiple variables, of any of the terms. So the greatest power here, in this case, is our degree. So our degree here is 5. And our leading coefficient is 3. And this polynomial is in standard form because the powers go from biggest to smallest. So in the standard form, the powers go from largest to smallest degree. All right, here's an example of another polynomial where you have to find the degree. So for example, if I have a polynomial like 3x to the fifth minus 2x to the eighth plus 3, well, this polynomial is not in standard form because 5 is smaller than 8 and 5 is written first. To write this in standard form, you're going to write the 8 power going first. But in any case, this is the degree of this polynomial. So the degree of that polynomial is 8. All right, so let's classify polynomials. So write the polynomial in standard form, identify the leading coefficient, the degree, and the number of terms. So for part A, so this right here, there are 3 terms to this polynomial. Right? So there's 1, 2, 3 terms. So that's actually part D. So we'll, let's see, we have A, B, C, and D. So we'll just say that we have 3 terms. A polynomial that has 3 terms is called a trinomial. Okay, so a polynomial with 3 terms is a trinomial. A polynomial with 2 terms is a binomial, and a polynomial with 1 term is a monomial. So it's just 1 term, so it's really not a polynomial, it's just a monomial. Alright, so right now this is not in standard form, so we know here that the highest power is 3. So our degree is 3. So this is a 3rd degree polynomial. All right, we also know that our leading coefficient is a number that is multiplied by the highest power of x. So in this case, the leading coefficient is 2. And then now we can go ahead and write this in the correct order. So the standard form, you write the highest power of x first, which is positive 2x cubed. The second largest, which is 4x, minus 4x. And then the smallest power of x, which is 9. So the power of x for 9 is 0. The power of x for 4x is 1. And then the power of x for 2x cubed is 3. All right, go ahead and pause the video, try the following two problems out. All right, let's go ahead and try it. So for part A, we want to make sure that it's in standard form. So the highest power is 4, and then the second highest is 3, and so on. So if we put it in standard form, well, we have a negative 3x to the fourth. We have a negative 5x cubed. That's the second highest power. We have a positive 2x. That's the third highest. And then the lowest is positive 6. So that is in standard form. What is the leading coefficient? Well, the leading coefficient is negative 3. It's the guy that is multiplying the highest power of x. The degree? Well, the degree is the highest power here of the variable, which is 4. So this is 4th degree. And the number of terms, we have 1, 2, 3, 4 terms. All right, let's look at part B. So let's put it in order. The highest power is 6. So we got positive 2x to the 6th. Then we have x to the 5th, positive x to the 5th. Then we have negative 3x to the 4th, negative 3x to the 4th. And then the cube, so positive 4x cubed. And then we have a negative 8x. So the leading coefficient is 2, the number multiplied by the highest power of x. The degree is the highest power, which is 6. And we have 1, 2, 3, 4, 5 terms. All right, that's all there is to it. Okay, so a polynomial function is a function whose rule is given by a polynomial. So this is, for example, f of x equals x to the third plus 2x squared minus x plus 5. So that's an example of a polynomial function. Remember that f of x is equal to y, right? So this can also be y. But this is a function rule, right, where the rule is given by a polynomial function. In this case, this polynomial is third degree. The end behavior of a graph describes what happens to the function values, which are the y values, as x gets bigger or approaches in positive infinity, or as x gets more negative, which means approaches negative infinity. So we'll talk about how to determine the end behavior. All right, so let's determine the end behavior of the following functions. So let's look at f of x equals x. All right, so what we want to do is we're going to graph these three functions on Desmos. So we have y is equal to, go ahead and type it in, y is equal to x. And then so let's look at y equals x first. So that's the equation, y equals x. Notice that the end behavior, as x approaches positive infinity, so this is how the graph kind of looks like. I'll do it over here. So as x approaches positive infinity, as x gets bigger, y gets bigger. So you see that pattern, as x gets bigger, y gets bigger. And then as x gets more negative, y gets more negative. So in that case, the way we write that for f of x equals x is as x gets bigger and bigger, which means approaches positive infinity, y gets bigger and bigger, more positive, so positive infinity. As x gets more negative, or negative infinity, y also gets more negative, or negative infinity. All right, let's look at the next graph, 0.5 x cubed minus x squared plus 3. All right, so now we got our next graph. So notice that the graph looks kind of like this, right? And notice that as x goes bigger and bigger, the y also gets bigger and bigger. As x goes negative, y also goes negative. So, which is the same pattern as y equals x. So the end behavior is the same. So this is the end behavior. All right, now let's look at the last one. 2x to the fifth minus x squared minus x minus 2. All right, notice that the end behavior for this is also the same. They're different graphs, but the behavior is the same. You have as x gets bigger, y gets bigger. As x gets smaller, y gets smaller. So right here, these are odd. These functions have odd degree, right? So this is odd degree. And these functions have a positive leading coefficient. The leading coefficient here is 1. The leading coefficient here is 0.5. The leading coefficient here is 2. So this has a positive leading coefficient. So the positive leading coefficient tells you a whole bunch about the function. It tells you if it's positive and the degree is odd, it's always going to have this pattern. This here, this here. So this is the pattern for an odd degree positive leading coefficient. All right, now let's look at the pattern for the next set of functions. All right, so here we have the degrees are odd. This is a 1 degree, this is 3, and this is 5. So this is odd degree. And this time it has a negative leading coefficient. So negative. So let's take a look at the behavior of these graphs. So let's graph negative x. And then finally negative 2x to the fifth plus x squared plus x plus 2. Now let's look at the graphs. So notice that the end behavior is opposite of what it was in the previous, right? It's completely opposite. So in this case, the pattern for the end behavior seems to be it starts going up on the left side and then it goes down on the right side. So that's the pattern for that. So let's describe the end behavior. All right, so just real quick, if you look at, the graphs, let's look at the green one. So as x goes negative, y goes positive. As x goes positive, y goes negative. So that's our end behavior. So let's describe that. So as x approaches positive numbers, infinity, y goes to negative numbers. As x gets more and more negative, y gets more and more positive. All right, now let's look at the end behavior for the third set of functions. So if you look at the functions, we have an even degree, 2, 4, and 6. So the degree here is even. And if you look at the leading coefficients, they're positive. So how do these behave? Well, we know how x squared looks like. X squared looks like a parabola. We'll draw it over here. All right, there's my second one in blue. And then finally, so now let's take a look at these. All right, so if we look at the red, looks like the pattern is they both start going up, right? They both start up on the left side and up on the right side. Same thing for the green, same thing for the blue. So if we were to describe this pattern, the pattern would be they would start going up on the left side and then they end up going up on the right side. That's the pattern you can kind of see, right? So like for this one, it's going up and then up, you know, on each side. So for this, as x goes more negative, y goes more positive. As x goes more positive, y goes more positive. So that's our end behavior. So as x approaches positive numbers, infinity, and gets bigger, y also gets bigger positively. As x gets smaller and smaller, more negative, y continues to go up, up, and getting bigger in the positive. All right, now let's look at the last set of functions. So notice here, if you look at the degrees are even, but the leading coefficients are negative. So we have even degree, negative leading coefficient. All right, so since x squared is a parabola and it's negative, we know it goes down, concave down. Now for the next one, it should also have that same pattern where it's kind of going down. And indeed it is. Now let's look at the last one. All right, zoom in on the functions. So it looks like they're both going down on the left side, down on the right side. So there's our pattern. So they start down on the left side, down on the right side. So if we were to do this, if we were to write out, you know, let's look at one of these functions. Let's look at this one over here. As x goes to positive infinity, y goes to negative infinity. As x goes to negative infinity, y goes to negative infinity. So there's our pattern, or there's our end behavior. So as x approaches positive infinity, y approaches negative numbers, infinity. As x approaches negative infinity, y approaches negative infinity. All right, so basically, we went over the 4 different cases, whether you have even degree or odd degree, versus positive and negative leading coefficients. So using these 4 patterns, or these 4 cases, you can determine the end behavior of any polynomial function, as long as you know what the degree is and the leading coefficient. All right, go ahead and try the following problem, pause the video, see if you can determine the end behavior. All right, so let's determine the end behavior and leading coefficient. All right, so let's look at part A. So for part A, well, we know that the degree is 6, right? So the degree is equal to 6. That's the highest power. We know that the leading coefficient is 2, which is positive, right? And we know that the degree of 6 is even. So we have even degree, positive leading coefficient. So therefore, the pattern is going to look like it's going up, up, like that. So that's going to be the pattern for even degree and positive leading coefficient. So if we were to write the end behavior, we would write it as, so as x approaches positive infinity, y approaches positive infinity, as x approaches negative infinity, y approaches positive infinity. All right, that's my end behavior. Now let's look at part B. So our degree is 3, the highest power. Our leading coefficient is -5. So this is odd degree, and the -5 is, well, it's negative. So if you look at our 4 cases, one of our 4 cases, odd degree and negative is going to look like, well, it's going to start up like this and then go down on the right side. So in that case, as x approaches positive infinity, y approaches negative infinity. As x approaches negative infinity, y approaches positive infinity. All right, and that's it for the lesson, guys. So you just have to be able to determine the end behavior, leading coefficient, so all of those features in order to ultimately, what we want to do is be able to sketch a graph using this information, or at least sketch, an approximation of the graph. All right, that's it for the lesson, guys. I'll see you in the next one.